Thank you very much for the introducing words. Shortly to me, I'm an aerospace engineer, and I would say I'm a real systems engineer. I was working 5 years in the aerospace business, developing a control system for a rocket motor from the very beginning, from requirements over architecture, testing, simulation, everything. So I'm a real systems engineer, and I'm glad that this track is called Smart Systems Engineering. It's quite funny because our pilot project is also called Smart Systems Engineering. I present this on behalf of my colleagues from ProStep and also from our scientific partner Claas Blume from Fraunhofer IPK. And thanks to Professor Gressler this morning, I added here the V model as the ProStep V model. Let's have a look to the content. First of all, I will give you a brief overview of what is ProStep. There's the ProStep Association and the ProStep AG, the stock company ProStep. Then I give you a brief overview of the Smart Systems Engineering project and the big picture. After that, just one single project result regarding to simulation architecture, and last in this short conclusion. So, well, let's see how that's right. Yeah, lots of animations. Okay, and actually ProStep is like 25 years old. We got the commercial part, which is a stock company. Our stockholders are Volkswagen, Opel, Bosch, Daimler, Siemens, Continental, Delft, and the ProStep Association, which is a commercial company. And we got the non-profit part, which is we call those ProStep organizations, we call ourselves like a think tank for digital transformation in product creation and production. The ProStep Association is a non-profit organization. We have around about 180 members. You can see some of the logos of our members. Basically from industry, IT, and research. We define standards, we are safeguarding industrial benefits, we're doing industrialization, we try to safeguard interoperability between the different tools, so we step on the feet of the tool vendors also. And yeah, we do IT standards and implementation of these standards. Within this ProStep Association, there are several projects, around about 30, and I'm the lead of the Smart Systems Engineering project. First of all, a little bit motivation for this project. Well, as we've seen during the whole conference, the time of machinery is over completely. No? And so nowadays, a product has at least mechanics, electronics, embedded software, mobile applications, cloud service, and so on. So everybody's talking about cyber-physical systems, and this is now reality. I mean, a light bulb like 10 years ago was a little metal thread with the glass on top of it, and that's it. Nowadays, it's cyber-physical systems with actuators, with sensors, with connection to the internet, and so on. So welcome to the reality of smart products. Therefore, we have to have multidisciplinary engineering and product development, and thus we have multidisciplinary data and information. And nowadays, the competitive collaboration is getting more and more away. For example, the big OEM in Germany, like Daimler, is asking to develop a braking system from Continental. And Continental delivers the electronic control unit. And the control algorithm for this electronic control unit comes from Bosch, which are really competitors. So collaboration, if you look at the dictionary, it's called, it can be described as work together with your enemy. And this is getting more and more day-to-day life, that we work together with our hardest competitors. And this is especially in the big industries. in the aircraft industry, in the automotive, and also in the shipbuilding industry. So we as Smart Systems Engineering, we try to push further the state-of-the-art of virtual functional system development, verification and validation, and this in a scenario of cross-enterprise development. So I tried to give you the vision within just one picture, this one. Without any words, this picture shows you what is Smart Systems Engineering, what we do. Well, we got two partners, two different partners. Partner A could be an OEM, and partner B could be a supplier. And each of these two partners, they have a V model. Nowadays, Automotive Spice makes you to have a V model for the development. And nowadays, the OEM doesn't only want CAD data and the product itself, the subsystem of the car. Nowadays, they want a virtual prototype, functional prototype, to integrate in the overall system and see if the car brakes sufficiently good, right? And so, basically, we as Smart Systems Engineering, we are caring about this, about the data and information exchange between the two cooperating partners. This is Smart Systems Engineering, this is our project. So our consortium, we have around about 30, we've got 29 project participants from industry, from academics, and from the IT vendor side. We are a user-driven project, so we got 44% of users. So we take the requirements, the demands from the users, and try to convert them into best practices and recommendations. You can see the list of our partners. You see there are most of the big OEMs in Germany, most of the big suppliers, and we also got the aerospace industry with Airbus. Our project organization is the following. We got 6 technical work package, and I'm the lead of the project management work package, together with the godfather of the project from Gran. Today, I will just give you a brief overview or some results from the work package 2, which is industrial building blocks in simulation architectures. I think this will really fit into the next presentation from Stjepan. So yeah, short overview of the other work packages. Work package 3 is called FMI industrialization. FMI is the functional markup interface, which is kind of a neutral format for the exchange of simulation models and for doing co-simulation. And this FMI standard was standardized by the Modelica Association, and we as we took this standard and took the user demands and did a kind of industrialization of FMI. So we pushed it into the industry, to the users, which started as an academic project. It's now being used in the industry widely, in automotive, aerospace, and the shipbuilding industry. Then the work package 4 is about system-level challenges of interdisciplinary collaboration. Work package 5 is about data management. I'll show you a little slide about this. Work package 6 is very important about IP protection, because if Bosch sees what's exactly within the electronic control unit of Continental, that would be not so good for this competing partners. No? And the last work package falls a little bit apart from this. It is about virtual electronic control units, about if we need new standards for this. Because nowadays, with the e-mobility, electronic control units are getting more and more important with cars. Nowadays, a car has around about 70 of them, and they're getting more and more and more. And for the verification and validation of VDs, ECUs, and of networks, the question is, do we need a new standard in this topic? Okay. Now we got our famous SMARTSE, Smart Systems Engineering V model. I don't want to go into detail. This is after Brenda, as I've said in the morning. And well, we as ProStep, we see more or less three big challenges in the V model. Well, what's working really quite well is here on the button, where we got the three different disciplines, and on the component level that works out very well. Here on top, there has to be something to describe the overall system. Thinking of cyber-physical systems, how can you model this, and how can you simulate this? That's one of the challenges. I would say the second challenge is the granularity, going from top to down, doing systems engineering. This is the second one. And the third one I see as the virtual verification and validation of the product itself. But this was just a small excursion. What we did, we used this V model and allocated the use cases from our users, from the companies. And we found out 11 use cases, mostly in the software domain and in the mechanical domain, and allocated them on V model. And then we took these use cases and put them one level lower, so we detailed them. We had a kind of an ID0 of these use cases, and then we took these use cases and created a smart systems engineering reference process, which is, here you can see the swim line diagram with the different partners. I don't want to go into detail, but what's quite interesting also for you, we are currently developing accompanying templates for this collaboration between different partners, which we call simulation model metadata. So this is kind of an XMI file which reads and writes into simulation models. And for example, there was a big OEM who took a simulation model, and which was for the development of a system, and used it for crash simulation. And I mean, this can't be, right? So this SMMD has general information about model content usage and usage information, model execution information, and model implementation information. That these models are used where they should be used. Now let's have a look to the work package. Three? Okay. I'm the bad guy. I got 8. But okay, let's have a look to 5. Isn't it a big negotiation? What we did is we created a generic system model. In our case, we did it for highly autonomous driving, for HAD. No? And here we got the environment, we got the electrics, electronics, and the physical structure. And we said, okay, we need the environment, we need a battery, and we want to simulate an electric motor in this case, right? And then in the next step, we have the so-called purpose-oriented simulation system architecture, which we also call them a 4-layer approach. In the next slide, I will show you this a little bit more into detail. And so we come from top down, we do real systems engineering. Instead of like starting to simulate something and then we wonder what did we simulate and how does it correlate? No, we do it top down, we do a generic system model and break it down until we got at the end, we go to the simulation model. So here's an overview of this 4-layer approach. We start with the overall layer where we got very rough and system overview. We of the engineering problems, we got the physical and more or less the functional architecture, and so we can see what are the borders of our system, where are the problems. We do kind of who's collaborating in which part with whom. That's basically the first level. In the second level, I can show you afterwards. The next slide is kind of a detail of this second layer, is the topology. No? So we have a closer look to the relevant subsystems, the cause effect chains, and so on. So we get a clear understanding of the simulation and the requirements. On the third level, we already go deep into detail. So we define, specify the simulation tools, the coupled simulation, co-simulation, and so on. And the last one, the layer 4, is the resimulation model itself. Here's an example of the HAD for the layer 2. So you can see Okay, 2 more minutes, or what is it?
No.
Okay, mine's, here you can see, we got the environment basically, we got the sensors. The sensors we would implement, we would ask, the OEM would ask to the suppliers to supply a model of the sensors within an FMU to do it. Then we got the functional chain itself for the autonomous driving, and here we can see already the angle wheel and the actuation capabilities and the acceleration and so on. Here we get actuation system, we got the driver model, the vehicle model, and this we got the overall simulation scenario in this level 2. Let's go quickly over the conclusion. Well, we as smart systems engineering, we have to focus on collaborating in cross-enterprise development scenarios. As I've said, we've seen the presentation of our first keynote speaker today, Professor Cecile. He said, collaboration, collaboration, collaboration. This was a quotation of him. If a company is not able to collaborate, he will be dead in 5 to 10 years. That's not for me. So yeah, exactly this is what we're working on. We don't create standards. We do recommend. We do recommendations. We publish best practices. We are very close to application projects, but however, we are pretty competitive. We don't help Siemens or Daimler or whatever to do something. If not, we just give the framework to do it. And of course, we are very result oriented because we are financed by the industry, right? They want something for their money. 2 weeks ago, we released our recommendation, SMARTSE recommendation 2. You can find it on our website. And what's new? As I said, we've got IP protection, model data management, simulation architecture, which I've shown you a little bit today, simulation tasks and clustering of simulation tasks, which is also very important. We gave an overview of systems engineering formats and standards, and the need of virtual electronic control units. Well, we as SMARTSE, we are very automotive. We are very strong in the automotive sector. However, the ideas, this business case is just an exemplary, and it can be transferred also to other industries, as we've seen to the aerospace sector, and also to the shipping sector, and also to other sectors. Oh, it's just an overview of the recommendation. So this is a very document is like very concise of 60 pages, and if you want to go into detail, there are 180 pages roundabout with lots of annexes. Okay, so thank you very much for your attention, and please feel free to ask me something.
Yeah, so I think there's one question right now, because otherwise we keep it to the end.
You mentioned something related to the V model. Do you think that the V model is really good for modeling smart systems?
Well, do I think it is really good? I think it gives you, as I said, from the top you can go down, and from the bottom you go up. And this is
I believe smart systems are compositional by nature, not composable but compositional by nature, because otherwise they cannot build, for instance, awareness, they cannot reason, they cannot adopt themselves, because here exactly the problem is that the traditional composable systems were not adaptable in a sense. Either you build in the adaptation facilities and then you changed it, but they are definitely not intended for self-driving. You are so active around me today. So actually they are no self-adaptation. Like the nature of the smart system is the self-adaptation, right?
Yeah.
So, and this system, if they do need to implement this particular self-adaptation, they cannot be composable. That is my fundamental problem with the whole V model. Maybe it is, how to say, we try to save it, and instead we need to have a different model just for the reason to capture this compositionality, where what I mean by that the system operation is not a result of the additive operation of the components. Like in case of the composable system, I apologize for that, but I really would like to know your opinion because...
Let me answer this with the quotation of Winston Churchill. He said, democracy is really shit, it's really bad, but it's the best we have. So if you show me something which, or it's an open question, if somebody shows something which is more appropriate to resolve the development question than a V model, I would be really pleased to find that.
It's not so difficult, please. I believe that if you consider non-reductionist models, we are one step further. Because the fundamental philosophical assumption is that our systems can be reduced to individual self-contained components, right? Now, if we reject this and we say that the reductionism principle is not working, or we don't impose that principle on systems, then I believe we can develop something which might be a circular model, you know, because this is how, when you change something here, you have to know how other things are influenced other places. It is exactly the same story as we went from the linear model to the let's say, obviously, with all respect to the German researchers, to the water flow model, you know, and then came all kind of branching model, and now we are already in the past finding model, you know. So
the question is, exactly like agile product development, where you got very, it could be a kind of a spiral model where you really build it up.
Exactly.
And in the agile is not only, well, I had recently a workshop about this in 2 days, and it is not only for software development. You could use it for hardware, you could use it for documents too.
And knowledge.
Knowledge,
which is not decomposable.
I said it. Okay.